is Kirtana Kumar, and this is my lab report 4 about the measurements of a magnetic field of a bar magnet. The purpose of this lab is to measure the magnetic field of a small bar magnet depending on distance and to compare those results for the on and off axis magnetic fields based on the Biot-Savart law. The overall experiment setup uses a magnetometer app on the phone, a meter stick, and tape to measure the magnetic field of the bar magnet. Afterwards, a model is created through code to compare the off-axis magnetic field with the experiment. The system here is the magnet, and the surroundings are everything else. For overall results, the calculated magnetic dipole moment was mu is equal to 2.15, and the linear relationship between magnetism and distance from the magnet is shown here, which follows this equation given here, where natural log of the field is equal to natural log of k plus n times natural log of distance. And then the calculated off-axis magnetic field is shown here, and based off the code or the model, the off-axis magnetic field is given here. So the main physics ideas in this lab were Biot-Savart law and the magnetic dipole field. Biot-Savart law, in short terms, states that the longer the distance is from the source, between the source and system, the weaker the magnetic field will be, and the closer the distance is between the source and system, the stronger the magnetic field will be. It is also represented over here with magnitude of, or the K magnetic constant, current, and length of the source as a cross product with r hat all over r squared. And it is used to predict the magnetic field for both the on and off axis fields in the model and comes in this form. And then additionally, B-dipole also uses this formula to take into consideration all of the magnetic field rather than separating it into our parallel and perpendicular components, and this can be seen in the code. So for the experiment and model, it should be noted that the experiment had us calibrate our phone to compensate for Earth's magnetic field by aligning with north, and for the most accurate measurements to find the magnetometer within our phone, which is marked by this red X on this tape. The first part of the experiment had us follow the model in the upper right and record the distance at certain strengths of the magnetic field, so 20, 70, and 120, etc. microteslas. And then using the data points collected, a linear relationship was formed in order to determine the value of n in this equation, where n is the slope. And mu is then calculated based on this equation, where k is equal to the k magnetic constant times 2 n mu. So this is the data that was collected from my phone. And as we can see, with the magnetic field and versus the distance as a linear version, the graph has an overall negative correlation, since being farther from a magnet results in a lesser strength of the magnetic field. And then based on the equation, n is equal to negative 2.8. And when solving for mu using this equation, we receive 2.15 as the magnetic dipole moment value. The second part of the experiment follows the setup seen on the right, where we find a distance where B net is equal to 100 microteslas along the x-axis, and then we move along the y-axis to have the same distance along the y-axis to create a distance d from the magnet, and recorded all the bx, by, bz values, and take into consideration Earth's magnetic field. And this data can be seen over here. This part of our experiment is used to compare our results against our coded model. So this is my coded model. So each arrow uses the dipole B portion of the program seen above that uses the magnetic dipole formula to calculate the magnitude and direction of the magnetic field. Cyan is perpendicular, orange is parallel, and magenta represents the overall magnetic field based on the experiment on the previous slide. And then these were the values found as B at 45 degrees at distance D. So assumptions and possible sources of error. In this experiment, human error is a major consideration when measuring the field using measuring tape and finding the accurate location of the magnetometer in the phone, and also when aligning with north. Additionally, the computational model doesn't consider Earth's magnetic field, so that is something to consider when our values don't align. So additional questions. If the magnetometer wasn't oriented to compensate for magnetic north, then Earth's magnetic field would have had a large influence on the measurements of the magnetic field and distance, and then this would result in skewed measurements that would not be very accurate. And if two magnets were stuck together end to end, they would act as a series in which their magnitude or strength of the magnitude moment would double, which in turn would double the magnetic field since they're proportional.